Hi, everybody. Today, I'd like uh, talk about a little bit about the today's topics. Actually, today we have this one is a workshop of Kayak Gakkai, and also this talk is the Professor Ashwin Chinnayya is going to talk about the one of the KGRI lecture series. The title is Computational of Gaseous Detonation Wave with Losses. And first, let me talk about KGRI. It's Keio University Global Research Institute. Keio University Global Research Institute, KGRI aim to promote international research and educational exchange and invite those working in the forefront of the research and education in Japan and overseas to give lectures. On this occasion, Professor Ashwin Chinnayya from the ISAE-ENSMA, École nationale supérieure du mécanical et aéronautique. In France, we give a lecture entitled Computation of Gaseous Detonation Wave with Losses. First, let me talk about a little bit about Professor Ashwin Chinnayya. It's now, as you know, the Professor Chinnayya is an expert in detonation and computational fluid with a special interest in non-ideal detonation confined by inert gas layers. He holds a professorship of ISAE-ENSMA Poitiers Institut Pprime, fluid thermal combustion department detonation team, and is head of energetics department of ISAE-ENSMA. This year, he is a distinguished guest professor global at the Keio University in Japan. This is a summary of his talk, but actually we are going to hear this talk. Maybe I don't have to talk about that. He's going to talk about maybe 45 or 50 minutes, and then we have a discussion 10 or 15 minutes later. Thank you.
So thank you very much, Professor Matsuo, for the invitation. My talk will deal with computation of gaseous detonation with losses. I have first to thank all the co-authors of this work, the PhD students, which are Maxime Reynaud, Saïd Taleb, and Ali Gousso. And also, I'm indebted to my young colleague, Rossier Melguizo Gavilanes, which is a member of the team also. At first, I will just give a general introduction. And of course, you all know that detonation have application in three main fields, which are propulsion. Here we have a nice image from the Nagoya University about rotating detonation engines, which has been mounted on a railway. We have also in defense. Here we have an example of fuel-air explosion. And also in hazard. There's a photo of an accident which has been held in Toulouse, in the southwest of France, in the beginning of 2000. So main application, propulsion, and I will mainly talk, my motivation come mainly for this talk from the rotating detonation engine. So the context, you all know the rotating detonation engine here. So there's a photo on the left, which, so we get in an annular chamber, we get an injection at the bottom end, and so we have a detonation which propagate at the circumference at the bottom, along the circumference of the annular chamber. Then downstream of the detonation front, we'll have high pressure burn gases, and of course, this will produce, the expansion of these gases will produce the continued thrust as everything goes very quickly. Of course, here you have two images from simulation. And from the simulation on the right, from the Matsuo group at the Keio University, you can see that in the RD, the flow field is highly non-ideal. You have, of course, partial mixing of the fuel and oxidant here. You have, of course, the mixing of all this premixture with the burned gases around there. And we have also some geometric problems about the chamber curvature, right here. And this will be the main topic of my talk, is the confinement by burned gases. In fact, the detonation here, which is propagating, propagates with premixture, but you have also burned gases here. So, main topic. I will make a recall. Watanabe, just before this talk, also gave this explanation. So the detonation is very simple, in fact. In the laminar case, laminar-Zaldovich-von Neumann-Döring modeling. So we have a leading shock wave, which is propagating in a gaseous mixture composed of fuel and oxidizer. So we have an increase of pressure and temperature, such as there's an induction zone where a radical will proliferate, and then you will get a reaction zone where the heat release will accelerate the flow until sonic location. And the sonic location here is the Chapman-Jouguet state. And from this little sketch, we can guess that there will be 3 characteristic length scales. First, 2 of them come from the chemistry, the induction and the reaction length, and then you have the hydrodynamic thickness, which is the distance between the shock here and this sonic plane. Downstream of this sonic plane, where Mach number in the shock frame reference is 1, you have rarefaction wave, and all the relaxation of the Chapman-Jouguet state to downstream flow. And of course, this depends on the system. Unfortunately, or fortunately for research, detonation front is multidimensional and instantaneous. Here, we get a Schlieren from Radulescu, which is a Schlieren taken of methane, oxygen, at very low pressure in a narrow channel. And so we can see that it is quite complicated. The leading shock is no more straight leading shock, but is an alternation of Mach waves and incident shock. The Mach wave is much more important of strength than the incident shock. And of course, there's also transverse waves of weak amplitude, which we can guess here. Of course, the Mach here, Mach wave, incident shock, and transverse wave intersect at the triple points. We can also see that there are spotty regions here. These spotty regions are unburned gases, and which will be burned after downstream within the hydrodynamic thickness. Of course, all the trajectory of these triple points will give the classical cellular structure of detonation, which is, in fact, the cell structure is some kind of instability length, which can be correlated to the induction length. This is just to show, but of course, the picture is much more complicated in 3D. We have transverse wave. Here you have 2 marginal cases, and here the rectangular mode, and here the diagonal modes. You have transverse waves of much higher strength. You have lines of triple points, and you have transient jets. You can see there appearing, which are very high amplitude. Here you get, at the middle of the photo, here you get a transverse wave, which is impinging on the leading shock. All these detonation, of course, are subjected to boundary conditions. And boundary conditions can affect the detonation. You have dissipative effect, like wall friction and heat transfer. You can have variation of area, the section, so it can influence the propagation of the detonation. As a consequences, you have losses. And this manifests as a velocity deficit as compared to the ideal Chapman-Jouguet value, which we talked about before. And eventually, it will lead to quenching of the front. So what we want to understand is what influenced the detonation front structure and its characteristics, and let's say what would be the range of existence of the detonation somehow. So for that, we will use a canonical configuration, which is the detonation propagation bounded by an inert layer. So here we can see the sketch, the canonical configuration, the Dabura experiments. So here we have a channel which fills the gas here. This straight line, black line, is a Miller film which separates the mixture from the inert gas. Of course, then there will be propagation of the detonation here. High pressure downstream of the detonation front will break the Miller, and you will get an oblique shock which propagates in the inert layer, and then you get separation from the inert layer and the burn gases. Of course, this has been deflected, and you get the interface here between burn gases and inert layer there. So this is the general picture of all the scope of my talk. The sketch here, which comes from Summers and Morrison, same group as Dabura. So here we get the shock front, you get the oblique shock here. Downstream of the shock front, of the detonation front, you get the reaction zone in this very slight thickness here. Then you get interface here. So you have a high pressure there and low pressure in the inert gases. So what happens is that you will have a deflection of the streamlines here. This deflection of the streamlines will lead to a curved detonation front. So you have a little curvature here. And of course, as downstream of the shock wave, oblique shock wave, you have a supersonic flow here. So you have to accelerate the flow from the sonic plane here up to this supersonic flow downstream of the oblique shock here. So this will be done by rarefaction wave. That means Prandtl-Meyer expansion waves, typically. And of course, what happens is that due to these expansion waves, the expansion waves will cool down the reactant, and then it can lead to quenching if there's no coupling between the reaction front and the detonation front. And so that's why these expansion waves are very important. So based on this canonical configuration, we will do two things. We will try to understand to which extent the chemical modeling can influence the interpretation of all this simulation, and we will try to understand to which extent the hydrodynamic thickness can be used as a characteristic length scale to characterize, to scale down all the results we will show. And then I will try to sketch two little things: influence of the equation of state on the cellular structure. For application, typically we can think about high pressure initial conditions. And I will try to see to which extent these, what we have learned here, what similarities we can have between narrow channels and this configuration, detonation, propagation bounded by an inert layer. So as for the numerical modeling, we will be using resident. So it is an in-house code for recycling mesh simulation of detonation. It is based on reactive Euler equations. We have high-order interpolation scheme, monotonicity preserving interpolation. We use directional splitting, HLS-Riemann solver, and also a fix for the shear waves, specific for multidimensional computation, MPI parallelization, and recycling of the computational domain. What does that mean? It means that what is of interest is what happens between the shock wave here and the sonic plane, which is located downstream. Or what happens downstream of the sonic plane will not interfere with the detonation process. So there's no need to compute the downstream flow. So each time the detonation propagates, all the computation mesh here will be erased and will be appended upstream of the detonation front. This allows to save computational costs and allows us to propagate the detonation in a computational way much longer than usual. So, first, influence of the chemical modeling. So, I have recalled here, here's a sketch of the configuration I will focus on. You have a height of fresh mixture in which the detonation will propagate here. This will have an initial temperature. For the first part, the temperature of the inert gas will be the same as the fresh mixture here. So you have the oblique shock, the interface, and all the cellular structure which takes place downstream the detonation front, rarefaction, the sonic pine. So at first, what we will try to understand is understanding of the non-ideal detonation. What does that mean here in the first part? It is quenching. What is the limit quenching? For that, we will vary the height of the premixture here and quote at which moment, at the critical height at which detonation does not propagate anymore. This is the first part. And then, as for chemistry, we will compare 3 different models. And then we will try to see the influence of the chemistry modeling on the quenching limits of detonation. And then, of course, we will try to see which one is the best as compared to experiments. 3 simple ones. The first one is a single step with constant gamma. You have fuel here, which deplete into reactant. So the simple one. And then there will be an Arrhenius law, classical one. You have also the 3-step constant gamma again. So you have fuel. The first step is initiation. So fuel will be decomposed into radicals, Y. So then we have a branching step. Fuel plus the radical will give again radical. So this helps the radical to get increased, the amount of radicals. This increases rapidly the amount of radicals. And then there's a termination step, Y, which gives the reactant here. And only the 3rd step is here, at least in our case, is exothermic. And then the classical one, detailed chemistry with Janov thermodynamics table. This one is very classical here. Okay? So then, yes. And yes, the mixture, I didn't say, the mixture we will focus on is hydrogen-oxygen at stoichiometric at 1 bar and initial conditions 300 kelvins. So what is the initial and boundary conditions of our computation? The first step is just propagation of the detonation with reactive mixture in a channel, very simple. And we have done it for, let's say, 100 microsecond. That means half a meter propagation. And then second step, we keep this the results and we put it as an input here in the configuration of interest, where we have the reactive mixture here of height h, and then inert. The temperature of the inert is the same as the temperature here of the reactive mixture. And of course, we want to mimic the experiments. The experiments is stoichiometric hydrogen with oxygen along with air in the inert, as an inert here. And so to mimic that with the single step and the 3-step, we have used, as suggested by Dabura and all his group, the ratio of acoustic impedance. We give it the same. Let us now compare the 3 chemical modeling. In here you have the induction time at constant volume combustion. You can see that the detail, you have a high temperature and a low temperature chemistry here with two different slopes. You can see that the free step has been, we can calibrate it quite well to reproduce the induction time. We have calibrated it with more accuracy in the high temperature range because we are dealing with detonation. So, and then we can see that the single step is not very good. It has been used to calibrate the cell size. It matches quite well the induction time in the high temperature range. But in the low temperature range here, beneath, let's say 1000 Kelvin, 900 Kelvins, not good enough, very, very bad. So this is usual, let's say. This can be expected because with the free step, you have much more freedom, degree of freedom, and so you can match the detailed chemistry very well. Let us come now to the instantaneous field. What happens? You can see that I have not shown here, but the cell size is approximately the same for all free chemistry. The propagation distance here is 0.1 meter, and the height is 13 lambda. You can see that the structure is very different here. The free step and the first step have islands of unburned gases here in blue. You can see it here. In the free step, there are much more. In the detail, there are no island of unburned gases. That means, in detail, it burns much more, much better. So we see that detonation structure changes drastically with chemistry modeling. So now we come to the quenching limit. The quenching height here, H, approximately a little bit higher than the critical height. You can see here for the first step and the free step modeling, also island of unburned gases here and there. We can see also in the detail, we come up with some unburned gases, and so more or less it is approximately the same. However, be careful here, the Y scale is completely different. It is 15 is here and 30 there. So when we come up to the quenching limit, it is very different. The critical height for detailed chemistry is much, much lower than that of the one step and than that of the free step modeling. So according to the chemistry modeling, you will have different critical height. So this is, yes, very important conclusion. So when now we come to understand which is the good one, we can see that with detailed chemistry, we can catch up the experiments. So we can recover the trend, very good correspondence of the numerical critical height from detailed chemistry models with that of experiments, 3-4 lambdas approximately. However, the quenching distance is also very different. 80 lambdas, 100 lambdas, and 45, 50 lambdas for detailed chemistry. So very different. Here I show a soot foil. So for detailed chemistry, a little bit above the critical height. We have here, we can see partial quenching, and then reignition here from the interface. And this has also been quoted in the experiment of Murray and Lee in '84. So the detailed chemistry, and also what surprises us is that the free step model was able to recover also this feature. The problem is we recover the structure with the free step and the detail, but we don't recover the correct critical height. let's look now, we just look to analysis of unburned pocket near the interface. So here, what looks the Schlieren of density near the, when we come up to near the critical height. So here we have an island of unburned gases. We want to understand what's happening. So we zoom. What we can see is that multiple shocks here is happening. So lots of shocks. And also, we can see that variation of the polytropic coefficient is very important also. 1.2 to 1. Quasi 1.4. So great variation. Now what we want is trying to understand what's happening. So we go back to the induction, here the induction time. So as I said before, we have a very good reproduction of induction time in the high temperature. And also, we have approximately the same cell size. Whatever the chemistry, you get the same cell size. And the free step matches very well the induction time. So it is not the good parameter to understand the quenching limit. So then we plot the thermicity rate, which in fact gives the heat, the rate at which heat is released in the flow field. And we can see that it is very different between the three chemical models. And the most pronounced one is that of the detailed one. Then what we have done is trying to understand the key parameter. From the key parameter, which is an instability, which is a parameter which characterizes the instability of the chemistry due to flow field perturbation. Here I've got the formula here. So it's the ratio of induction length versus the ratio of the reaction length. This is this ratio which is important in chemistry. And what we have found is comparison between these three of them, we got this formula. As simple as that. That means the critical height simplified, one step, three step, as compared to that of the detail, we can scale it with very good accuracy. The correlation was 0.992, something like that. We were quite surprised to find that. And of course, we have detailed chemistry to recover experimental data. So what is interesting from this comparison is that the key parameter enables us to scale up all the chemistry if we are only concerned about the quenching limit in somehow. This is what the proposed scaling, what come up with the comparison of these three chemical models. So this, okay, so this is the first part. Now I will talk about the hydrodynamic thickness. So what we do, as for the hydrodynamic thickness, is let's say we have a front. This is a snapshot. We will do it at the bottom for the rest of the talk. Here we have a bottom. So we keep track of this line at the bottom wall. Then as the detonation propagates, we change the initial, and then we average like that. And we average in time in order to get statistical computation on the fly. During the computation, we do it in the code. And so we have an averaging process in the detonation front frame. So this is very important. When we do that, so we know we have two cases, the stable case and the unstable case. This is idle computation for the moment with channel, typically. So in the stable case, the line is the ZND model. And here, the result of the computation. For the stable case, we recover the ZND model. This is natural because in the stable case, the transverse wave is not of very high strength. In the unstable case, we have the transverse wave are very high amplitude. And we see that there's a clear departure of the pressure, the mean pressure from the ZND model. 1D, 2D. 1D, there's longitudinal instabilities. In 2D, we add transverse instabilities. And more instabilities we put in the system, the more there's a departure from the ZND model, which is the laminar case. So, and then the hydrodynamic thickness here is the place where we have Mach 1 and is no more correlated where at the point where reactant is completely consumed. This is different now. So now we will complicate a little bit the computation. So the same canonical configuration. And what we do now, so we have also the height here. We will change the temperature of the inert gases, because in the application, the temperature of the inert gases, of the gas is burned. They represent burned gases. So we will try to increase it. We will increase it to 750 Kelvin and 1,400 Kelvin. And then what we will add also another parameter. We will change this ratio, the sensitivity of the reacting mixture, which is here the reduced activation energy. So if we count everything, we can say that the velocity deficit here is a function of these three parameters. What happens? Here you have the classical point of view. You have expansion wave towards the inert layer. So you will have a reduction of the detonation front. You have here, you can see a globally curved detonation front here. Here, instantaneous field, mean field, and you get the oblique shock front here and there. And you have the interface between burned gases and inert gases. Here, what we can see is that, I will try not to, in white, if you can see here, you have the sonic line. So the hydrodynamic thickness will be measured here, at the bottom wall here. And of course, from the mean picture here, we can get also the mean radius, the mean curvature at the bottom wall only. These two values. However, what happens when we increase the temperature? Here, this is the classical one I'm recalling. But when the temperature of the inert here is increasing, what's happening? The velocity here also increases, because the sound speed, when the sound speed of this mixture is getting higher. So what happens? We get an oblique shock. The oblique shock wave becomes a detached shock here. And then we get a jet here of inert, the reactive mixture doesn't burn here, doesn't burn anymore. And you have this oblique shock. So you have really a change of topology. The topology of the flow field changes. If now I zoom here, in that particular region, you get the detached shock here, you get a jet of gas, and you get also, because you have to, here you have the detonation front, and you have to match the detonation front with this detached shock. So this is done with a double oblique shock here, just here. That's very important, this numerical clearance. So this similar structure has been observed for detonation confined by a lighter gas, because here high temperature gas means high velocity. We can do it in experiments. That's what Dabora and Adams have made with helium. And they have shown here the same structure that we are talking about here. Here we can see the jet and the detached shock, which leads, in fact, the detonation front, which wants to go a little bit further than, much more rapidly than the one of the detonation. Also, this has been shown not également, but also shown in numerical study of WIM and Févisson. And when you look to numerical simulation of RD, you have also that. This bulge always in the detonation front, if you look carefully of simulation done by RD. So what we have a lot of data. We want to scale this data. Remember that there are 3 parameters. The problems depends on 3 parameters. So according to the Wood and Kirkwood model, or every model, you scale the deficit of detonation here, and you do it with the induction length, or half reaction length here, divided by radius of curvature of your system at the bottom wall. You can see that the data are very scattered. Look here. You could put that in log scale, in fact. You have a 0.1, 1 over, yes, very low data and very big here. Now, if you use hydrodynamic thickness, so you just change that with hydrodynamic thickness, which you can get from the numerical simulation. The data are, you have 2 curves. You have here the curves which is related to the regular mixture I've shown you before with very low activation energy. And you can plot almost a line here. All the data collapse on one line for the unstable mixture. You have one line for stable and another line here for unstable. Everything collapses. So what we can say that at first we have 3 parameters, a problem with 3 parameters. We can also almost say that the deficit of velocity is a quasi-function of the hydrodynamic thickness over this ratio. At least we have 2 curves for stable and unstable mixture. This is preliminary work, but we just try to do it in 3D also with one step. So here are the parameters of the computation. We have only done one computation. And of course, we only have 5 points per half reaction length. Here is one instantaneous field from temperature, the Schlieren of that, and here the mean structure, at least from what we have been able to do. And this is the average pressure field. So you can get here the radius and the hydrodynamic thickness at the bottom wall. We plot that on the same graph. What surprises us is that these are 2D computation. We can do lots of that. But when we put the 3D, it is just in line with that. So it seems that when we use the hydrodynamic thickness, which changes, of course, according to the parameters, but if you use that scale, it seems that the phenomena seems to scale linearly with hydrodynamic thickness, front curvature, and velocity deficit, but independent on dimensionality. That means all the data collapse on the same curve. Seems to do that. Of course, 3D, what we have seen is that 3D enables the detonation to be more resilient to losses. That means you see that we can go a little bit further here. This is due because you have much more transverse waves. The jets are much more important. And so it increases the probability to get hot spots. And so help detonation to propagate. So that's why I think that the aerodynamic thickness can help to scale and understand what's happening independent. And it seems independent of several of the modeling of chemistry and also of the dimensionality of the problem. Now I come to the influence of the equation of state. This is another work which we have done very recently. So most work are done on condensed phase or ideal gas regime. So ideal gas regime, let's say below 1 kilo per cubic meter, and for condensed phase, very high density. In between, less work. But this can happen if we have initial high pressure, either for safety storage or if there's let's say, a compressor in the RDE in the long term. So the objective of this little work, investigate high pressure effect on the multidimensional structure of gaseous detonation. This is very fundamental. So what we will do is just use Noble-Haber equation of state. This is the simplest correction to the ideal gas law. So you see, very, very simple to change, a covolume. This is used in high pressure combustion, for example. This is the first step. What is the influence on the cellular structure? Very simple. I just recall the reactive Euler equations. All these equations are classical. We will use one-step model, very easy. The ideal gas law, this is already coded, implemented. So very simple modification in the code, we just add that. And of course, the sound speed have to be modified because it has influence on the CFL number. But the modification is very, very little to do in the code, any code. We use same mixture property in order to make the things similar. Equation of state, what happens? Here, Noble-Haber, you can see very regular cellular structure here. And much more regular than the one from the ideal gas. Here you can see much more smaller cells. Here, cells appearing, cells disappearing here. No such feature, or less feature like that in the Noble-Haber. So the question is, where does that come from? The irregular cellular structure becoming much more regular. So we make a sulfoid close-up. Noble-Haber, very regular one. Ideal gas law. We observe what Radulescu called a cell bifurcation here. Here you can see that, here, just follow the blue line, we see that a detonation cell is being created here in the blue line. So we want to understand where does that come from and why is there this cell bifurcation. So we go back to a marginal case. Marginal case up the classical picture of one triple points here, which is impacting the wall and then going back upward. In the ideal gas, what happens is that you have a reminiscent here. You have a little slip line here. This slip line then interact with this complex, these triple points. It comes there. And then it's strengthening. Its strength is getting greater and greater. And then, at the end, it becomes a new cell, a new triple point. That means a new cell is being created. So what happens is that overall, you don't have cell bifurcation in the Noble-Haber case, but slip line interaction with a transverse shock wave gives cell bifurcation. Let's try to get that, cope that with the quantitative analysis proposed by Mach and Radulescu. They have made an analysis of an experimental database. So they put about 20 or 30 gaseous detonation, and they analyzes the polytropic coefficient. And they saw that there are cell bifurcation when the polytropic coefficient is below 1.3, and you get a cellular structure which is regular. And when it is higher than 1.4, it is irregular. This is a pure database analysis. But what would be the analog in our case? So we use the isentropic coefficient, which in the case of ideal gas is exactly the same. So here from ideal gas law at fundamental state, I make a mistake. The coefficient, isentropic coefficient here is 1.2, so it is below 1.3, it is irregular. I'm sorry about the little mistake in the slide. But for noble-able at the fundamental state, the polytropic coefficient is 1.4, so higher than 1.4 here. So also mistake, but regular. So from the analog of this analysis of Mach and Radulescu is the isentropic coefficient. So as for the influence of the equation of state, the comparison between ideal gas law and noble-able, simplest modification of high pressure effect, with the same chemistry modeling, we have more regular cells from the presence of high pressure effect. So the mechanism which we think is at the core of this is the interaction of slip line with a transverse shock wave correlated with the increase of the isentropic coefficient. And as a potential application, this of course has to be quoted, I think that we know empirically that detonation, transmission, and propagation depends on cell regularity. That, for example, the critical diameter is 2 times when it comes to regular mixture, 2 times more. So that means that when we want to scale something at high pressure, what happens in the ideal gas case, we have to take care when we come up to high pressure. If we want, for example, to scale an RDE or an arrestor, we have to think about that when high pressure effects come into play. At last, I would like to make a little sketch on narrow channel, and very rapidly, and show the link with narrow channel and the detonation configuration I've been talking about just before. So here, this is 2 mechanisms. The first from Manson and Guénoche, and then the second from the Fay model. Manson and Guénoche, they said that the reaction at the wall boundary was inhibited near the walls, and they made this sketch. That means a leading shock here and a Chapman-Jouguet plane just here, just like that. This is a sketch I quote from this paper. And so all the leading shock here is sustained. The propagation of the leading shock is sustained of what is in that zone. That's what they said. In the Fay model, a little bit different. The CG plane is here. And you have, because here you have to think about it in the laboratory frame. So here the wall is getting much more rapidly than the velocity in the core of the flow, which will lead to a negative boundary displacement. And so the streamline divergence, because we have to think about negative boundary displacement, that means that you have an area increase And this area increase leads to a divergence of the streamlines, and so to the detonation velocity deficit. So to get the simulation of that, we have used a shock wave model at the Korea lab, which is a Navier-Stokes multi-species reactive 2D model. Classical thing, Janov table, all mixture laws are here, or recall. As for the numerical model, it is a Weno 5. And diffusing flux just centered high order scheme. And, but for simplicity, for the chemical mechanism, we have used one-step model, even if the thermodynamic was representative of propane-oxygen at stoichiometry, the source term is very, very simple here in order to understand the structure of detonation. That's what I'm interested in. Here it leads to a stable detonation. What happens here? This is a velocity flow field. You can see this, I have put that in the laboratory frame of the shock, of the leading shock. You can see a high leading shock here, velocity, decrease, then it increases due to heat release. At the boundary layer, the velocity, at the wall, the velocity is much higher, of course. So you have expansion and acceleration of burn gases in the core flow, and the slip conditions will induce a boundary layer growth, and so you get also, that's why you get supersonic flow at the walls and subsonic flow just down in the core of the flow. The white line is a Mach number 1. Here. Mach number 1. Mach number 1, here you have a discontinuity. So here it's quite a singular point, quite strange here, because it is intersection of the base of the shock and also beginning of the boundary layer and also the boundary layer and also the subsonic region. In order to understand that, because here everything is supersonic here, we have plotted the characteristic lines. This is the Mach line. So what we can see here, in white is the Mach lines. So we can see it is getting increased from 1 to 5 or around 5 or 6 at the wall. And you see that the characteristic line is tangent to this subsonic zone here. So and of course, what you can see is that the dissipative effect here are propagated from the walls to the sonic line. This is the characteristic. It tries to push this subsonic zone like that. This one. You can see it tries to influence it. And so it's tangent because it is the singular, it is Mach 1. But from these, we can we can plot the boundary layer thickness, the displacement thickness, the momentum thickness, and compare it to the sonic line, sonic location. Here you get the boundary layer, the momentum thickness, and the displacement thickness. Classical, 0, and then you have boundary layer, which is increasing. And what happens is that here in black, you have the sonic location. That means here, subsonic region, and then here, supersonic region. So if I plot that in a sketch, I got that. So I've got what Fay have shown. Let's say the global picture is a mix of what Fay, of the Fay model and from Mansoy-Guénoche. So you get a shock here. You get the sonic line, which is in fact the Chapman-Jouguet surface. And you get the growth of the boundary layer just here. Of course, from the Mach lines, what happens? You can expect here expansion wave because here you have Mach 1, and at the wall you have high velocity, much more high velocity. So you have an expansion of Prandtl-Meyer expansion waves, classically. What I found very interesting, troubling, let's say, now I have sketched exactly the same, but the detonation bounded by an inert layer. So what happens? You get the leading shock here, which is curved, globally curved. You get here the Mach line, and you have also the Prandtl-Meyer fan and the oblique shock and the interface. So when we compare these two sketches, there are same key features. You have the curved shock here, curved shock here. Sonic line here, sonic line here. Prandtl-Meyer here, and Prandtl-Meyer here. So, of course, the mechanism by which the detonation propagates is different. Here we have dissipative effect. There it is lateral expansion of the gas. So the initial cause is very different. But in between, you have the same key features. Shock, curved shock, detonation driving zone here, and a Prandtl-Meyer expansion waves. You always have that who comes at the end. So now, conclusion of all the different things I've shown. At first, I have studied through the influence of the chemistry. The quenching limit have been shown to depend on the key parameter, let's say more or less linearly. The hydrodynamic thickness can be used to scale up all the data as far as the propagation is concerned. And then the cell regularity can be, let's say, determined from the isotopic coefficient. So let's say you have the key parameters which come into play, the hydrodynamic thickness, and then the isotopic coefficient, and which regularly, as far I believe, regularly comes into play in order, it can help us analyze this detonation propagation. And of course, we have shown also that similarities between two very different problems of detonation propagation, which is one which comes from an hydrodynamic point of view, expansion, and the other one from dissipative effect. And we show that same key features, characteristic feature come into play. So I would like to thank you for your attention and acknowledge Keio University and some local agencies, French one. Thank you very much.
So now we have a time for discussion and comment for his talk. Do you have any comment and question?
Thank you, nice presentation. So you mentioned about the chemistry modeling. So you one step, three step, and the detailed chemistry.
Yes.
But I think that you use the reduced chemistry, right? So I think you mentioned the detailed mechanism, but I think just the Mabel mechanism, right?
Yes,
you use that.
Yes.
But I think it is already reduced chemical reaction.
It is already reduced?
Yeah, already reduced, I think.
So not that one, because it was for hydrogen oxygen. So it was the big one, I think.
I think that the chemical reaction is more, there is a lot of reaction is happening in combustion. So I think, did you try to calculate the detailed chemical reaction?
One,
yes.
No, I have not, because there's lots of, it's
a
quite
lot
cross.
of models.
Yes, we didn't compare with, for example, the Ong and Al mechanism, but I think that the critical height is about the same that the Mevel one, from what I've seen, I think, here. It is the same critical height. But we have not make the computation ourselves, no. But I know the critical height is about the same. So we expect that the scaling we propose would be the same, yes.
Thank you very much. Very fruitful, many important results, four important results.
Yes.
I am one of the most important results, hydrodynamic fixes divided by
The radius.
radius. So could you show me the graph? It's, all of the data is one line. So it's so impacted. Yeah. I would like to check. The left is induction length divided by the R. Okay.
And it is, what we have shown is that the induction length in our computation was the same each time. So we were very careful about that. We also showed that the cell size was the same. Yes, for the set of parameters we have used.
Proportional to the induction length.
Yes, exactly. Okay. So, and what is here, it's quite, I have not shown it completely, but it's very low here. Very, very low. So the range of this parameter is huge.
Yeah.
Then when we got to the hydrodynamic fitness.
Okay. So my question is how to measure by experiments in the left.
Okay, so
we did many kind of experiments like that.
There have been let's say Thomas has tried because he correlated the end of that means the end of the subsonic region, so the hydrodynamic thickness, with the decay of the pressure, because when
decay of the pressure
fluctuation, because when you look to a pressure signals, it's lots, and then when it comes to the expansion wave, so he said this is the sonic point. That's how he has done that, and also there has been Weber and Oliver, but they have put needles in the flow. So when there are shock, and then there will be a bow shock attached, and with films, they know when the bow shock disappears. So they said it is the sonic point. Of course, there's a little bit difference because in the laboratory frame, the sonic point is not the same as in the shock attached frame. But anyway, they got estimation of that because it is, it is 1 over gamma in the laboratory frame. So they said approximately 1 because gamma is near 1 in gaseous detonation. So they make estimation like that.
Thank you very much.
There have also been a last paper in the area just recently, but I didn't, it is Gamezo and all these people who have make also some measurement of the sonic location through imagery, through visualization also. With visualization, I think. But I have not gone through that paper yet. No, he was one of the co-authors, and it was in 2020. Just recently, and Pulidenko. Yes, Pulidenko and Gamezo with experimental people, but I forgot the experimental. Ahmed, I think, something like that. I made some.
Can I ask you? I have a couple of questions. So the first one is about the effect of our chemistry model. And you used the 1-step, 3-step, the detailed three model, and they have almost the same critical height?
No, they have very, very different one. Here, that's, I forget. This is approximately, I put that here. It's about 13 here,
Yeah.
3, between 3 and 4, and here it's about 15.
I see. Okay.
So very wide range of critical height.
Yeah, and frontal structure the model is also seems to me different.
Very
Yeah,
different.
so it means that there are to obtain the accurate or exact frontal structure of the detonation, it is crucial to use a detailed chemistry model.
Yes, but yes, this is the conclusion. But from practical point of view, it is with hydrogen, oxygen. For example, 3D computation, as far as we are concerned, we can do it with one step. Let's say with 3 steps also we could do it. With detail, it's very difficult because we don't have the computational resources. So what I think is that if we were able to calibrate the thermicity, not only induction, but also thermicity, by adding some ingredient into the model, we could get it. If I go back to the here, one of the key points, I think, is the fact that we have constant gamma here. Perhaps if we have change of molecular mass, molecular weight, sorry, we could afford to get the correct thermicity profile. So we have still room to improve the initial 3-step model, in fact. Because in the initial 3-step model, there are lots of assumptions. But I think we can release some of them. But for the moment, I don't know which parameter would be the most important.
Yeah, so it means that
and
fine-tuned 3-step model is maybe the best option in the year.
Yes, because what is interesting in the 3-step model is the possibility to get the low temperature chemistry.
Yeah.
This is very important for application, and yes, if you want to get even force flame, it's about here, post-shock state. So I think it should be, and this would enable us to go to heavy hydrocarbons. That's what is of interest.
Thank you.
Definitely.
Okay, I think. Okay, it's already we started 70 minutes. Okay, thank you very much for Professor Chinnayya.
Thank you very much.